Hi, good afternoon. Am I audible?
Yes, sir.
Okay, we'll wait for a few minutes and let's wait for some other people to join, and then we'll start at 3:05. Okay. In the meantime, if you have any,
Okay,
in the meantime, if you have
sir.
any doubts, you can ask or any comments, anything till other people join. All right, let's begin. I hope you are able to see my homepage. Is that correct? Am I audible? Can you
Yes, sir.
can you see my homepage? There's a
Yes,
page.
sir.
Okay, so let's get started. My name is Amit Bansal. I am a PhD scholar at Indian Institute of Science, Bangalore, and my department is Center for Nanoscience and Engineering. So that's a direct correlation with your course, which is Introduction to Semiconductor Devices. So I have some hands-on experience with that also. I worked in a gallium nitride group. Gallium nitride is semiconductor. We'll be encountering this quite a few times during our coursework, during our sessions, and here you can visit my advisor's webpage. So just a brief summary that what I have been doing is that, as I told you, my research work is on gallium nitride. So you can see some of the images that the work I have done. So you can see some devices that I have made myself. There is a clean room in the Indian Institute of Science in my department sense. So here I have we have shown some image. So basically my work is radio frequency devices. If time permits, maybe we'll touch in this course, we'll touch upon some aspects, some applications of semiconductors. So this is one semiconductor device that you are seeing, and if you can see on the bottom right, you can see it's 50 micron. The scale bar is 50 microns. So the whole device, you can see in the central region, is barely 100 or 150 microns, and the width is only 50 microns. I have been TA before on similar courses, fundamental semiconductors, and there are a few other courses that I have been a TA of. Most importantly for you is my contact details. So on the top is my institute email ID, amitbansal@isc.ac.in. But I would prefer you contact me on the letter ID, which is learnwithamitbansal@gmail.com. So any communication that you want to have, apart from the communication that you can have in the forum itself. Apart from that, if you need some specific doubts or you need some specific queries to be answered, academic, then you can contact me on this email ID. And the last slide, so I have this YouTube channel, so whatever we are talking about in our sessions, so I'll be uploading whatever we are talking about to this YouTube channel, and the link of which I have shared in the chat box. So just a second, let me admit other people. So if you can see in the chat box, you must be able to see I'll just, for the people who have joined recently, I'll just copy paste whatever I had written earlier. So first is my email ID, the next is my YouTube channel. So in case for some reason you want to revisit some of the things that we are talking about here, you can go to the YouTube channel and watch the videos. So other TAs will also be doing the same. So as you must be aware, there will be a session on Friday, and I think on Saturday, that's my first session, and I think if I'm not mistaken, this is session on Monday. So I would encourage you to just attend, at least in the first few sessions, just attend all of them as much as possible, and then you can understand which person suits you best. We have different strengths and different weaknesses. All right, so that's about that. And finally, one more thing from my side. So I'll share, as I told you about that, I have a YouTube channel. So I'll just go to that, and because I've been doing this TA shift for quite some time now, it's been 2 or 3 years. So as you can see, this YouTube channel, Learn with Amit Bansal, has 34 videos. Okay, and if you go to the playlists, so there are some gate physics solutions of some previous year problems, because I was a TA for that. So I have uploaded this gate physics live sessions. You can see, so I used to solve 10 to 12 or problems, or not 10 to 12, 4 to 5 problems of gate physics previous year problems here. And basically this is my second course, basic electronics course. So let's go here.
Good evening, everyone.
And so you can see that so there's a super nodal analysis, transient analysis, diode based circuits, half wave rectifier, common emitter, bypass capacitor, op amps, and so on, combinatorial circuits, sequential circuits, your JK flip flop, ADC and DAC converter. So if you are interested, you can go through that. I just want to bring this up, that I'll be uploading the videos, whatever we are talking about, every video will be uploaded to this channel, and you are free to visit that for some other things, and obviously for this whatever we talk about here. All right, so that's enough about myself. Let me just stop presenting for now. But before we get started, I need a few more details from your side. I would like to know the audience, and then hence I'll cater my presentation according to your needs. So let me just start. Let me just share my presentation. So just hold on a second. Yeah, I hope the screen is visible, right? Of the presentation, the PPTX file. Please respond.
Yes, sir.
Okay, thank you. So as you know, the course name is Introduction to Semiconductor Devices. The course ID is NOC23EE82. My name is Amit. I talked enough about me. I'm from IISc Bangalore, and this is the first week. We'll be together for 12 weeks, and hopefully there'll be a mini session of 1 hour where I'll, depending on your requirements, so whether you want revision of some topic or you want some summary of all the sessions, so whatever the requirement is, the 13th session will be according to that. So just a reminder, these sessions are 2 hours long. You can interrupt me at any point of time for your queries. I'd prefer that queries of which the topic I'm doing, as you know, week 1 is assignment is out, and week 1 lectures are also out. So I hope you would have viewed them, because and I'll be solving basically the problems from previous year assignment. Okay, not this year assignment, because the assignment is still due. So I would request you to, before joining the session or other sessions, you watch the videos so that you can get maximum out of it. And also, if you get the time, just watch the assignment that is due. Obviously, as I said, I cannot solve the questions, but if you have some conceptual doubts in them, for instance, what is a band gap? how can we change the band gap? Is band gap fixed for any material? What is that? So the questions will crop up as we go on into the course, so those questions I can answer. Plus you can take hints from previous year's questions which I'll be solving. And as I told you, you can stop me anytime. You're more welcome to do that. If you have some specific doubts, you can email me, as I shared my email ID. I'll do so again because people are still joining. I'll just copy paste. So this is my email ID, again I have shared. So feel free to contact me anytime, or you can use the forum, whatever you like. So that's that. Now I can see there are around I think 13 or so people. Okay, so I'll request you to raise your hand. I'm going to ask a set of questions. So how many of you are in your bachelor's? I'll take 5 or so minutes so that I can understand you, and because I'll have to cater my presentation according to that. So in your bachelor's, I can see 5 hands. Okay, 4 people have raised their hands. Okay, more. Okay, I'll wait for a couple of minutes. So that's 8 now. Okay, so out of, so predominantly bachelors. How many of you are in first or second year of bachelors then? Among the people, please, only please those first or second year. Okay, so we have, all right, so we have at least half of them as first or second year. Okay, that's fine. How many are of you in your, please put down, lower your hands. Second, the next question is, how many are of you in masters or higher? That means a postgraduate, masters or PhD. Okay, okay, we have 2 people like that. Fine. Okay, so I'll make sure that I can then I'll keep the level so that even first year, second year people who are here can understand that. And how many of you do not have a background in electronics? Not have a background in electronics? Okay, fine. So 4 people at least, it's fine. So I'll make sure that whenever I'm talking about any topic, I'll make sure that I understand that I have to talk a bit about the basics. So all right, that's fine. Now I would request you to just, I'll call you out by your name. If you feel comfortable, you can speak, and I want to know what do you expect of me. I mean, in this 2 hour session which I've been doing for, which will be together for 12 weeks. So I need to understand that what are your requirements from me. All right. So for that, I'll be calling out. If you don't feel comfortable talking, that's fine. You can write in the chat box. I just want to know the requirements again, so that I can help you and help myself learn. Because when you ask questions, I'll have to pick my brains and figure out what to answer and how to present in a manner that even the first or second year electronics people, as well as the MTech persons who are there, they can understand. All right. So I'll be calling out names alphabetically. So I request you unmute yourself, and just please tell me what are your expectations. Your which year are you in, which degree are you pursuing, or are you in a job? Just mention that about yourself, and what are your expectations from these sessions. So first, Anirudh Bhardwaj. Anirudh? Yeah.
Hello. Yeah, hi. I just finished my fourth year. I wanted to learn the basics more. That's why I joined this course.
All right.
Or maybe like solving the previous week questions would be very helpful.
Okay. Yeah, we'll be touch previous year questions. So for instance, okay, I should mention that. So for instance, your assignment due date is I think 8th or 9th of August. So when the solutions will be out, so and naturally in the forum we can discuss it. But if you have some specific doubts that okay, you don't want, you need a review of that, send me an email first. It's preferable because I'll then give special time to that problem. Okay. So I request you to send me an email. I've already shared. I will be solving questions. Anuj, please unmute and tell me something about yourself and what do you expect from these sessions.
Sir, I am Anuj and I am pursuing my BTech EC in second year. I am here to learn about semiconductor devices.
All right, all right. Okay, thank you. Joshika.
Hello, everyone, and hello, sir. I'm Joshika, and I'm doing my BTech. So I'm currently in third year, fifth sem, and uh, it's my minor subject, VLSI. So I'm very pleased to learn about the semiconductor devices subject, and also learn about the basics more here. So thank you.
All right. Kartike?
Hello, sir. I'm a BTech student of currently in fifth semester,
Okay.
and I have joined this course to gain a thorough understanding of semiconductors and what actually they are.
Okay. Okay. So I understand many of you who have spoken, they want to know. If it would really help me if you can tell what do you expect specifically of me. I'll be talking about concepts, but the detailed lectures are already there. So if there's specific requests from my side, for instance, I'll be talking about concepts as well as problems, both of them. But if there's specific request, you can speak about it now or maybe later when we are doing the questions. Okay. Sai Vikas? Okay, we'll focus on the problems. Rajesh? Okay. Rohan?
Sir, I'm currently in my third year
Mhm.
and I have problems. I'm expecting that I can solve the problems in this chapter better because I have problem solving physics problems like this.
Okay, okay. So I'll be talking about the how to approach the problems, and then you can take
Yes,
up your lessons from that. Okay, thank you.
thank you, sir.
Sagar?
Yeah. Hello, I am Sagar. Actually, I completed my BTech. I'm going to join in MTech.
Okay.
I have completed one NPTEL workshop on electronic system characterization at IIT Bombay.
Mm-hmm.
So I have learned some of the experiments, but with the less knowledge of the subject. So I want to know the more into the subject
Okay,
concepts.
okay, okay. We'll make sure you. I'll try my best
Thank,
to integrate. Saurabh? Saurabh? All right, that's okay. So my takeaway is that heavy majority of you are in your BTech, and a couple of people who have graduated and want to know more. So I'll be catering to that I'll touch upon the concepts, and more importantly, because many of you told that you want to see how to solve the problem, so we'll see that how to approach a specific problem. So it will be a mix of both, and as always, I'll keep repeating this. Feel free to stop me at any point of time. I'll be more than happy to answer your problems. So this is the first week, so we'll start very slow, and as always, the session that we are doing will be in direct correlation to the lectures that have been uploaded on the NPTEL by Professor Naresh. Conducted by Professor Naresh and uploaded by NPTEL team. So there will be a direct correlation between them. I would request you to not ask the questions from. You can, but other people might not have watched. So I can entertain your query. That's fine. But some other people might have some problems. But you feel free to ask. Uh, I'll try to answer the problem with the given knowledge that we have. Like for week 3 problem, if you ask me a question from week 3, I'll try to answer that based on week 1 and week 2 lectures that have already been uploaded. So that's that. Now let me share my PPT. So this we have seen introduction to semiconductor devices, week 1. All right. I hope you can see the question 1. Yes, please respond. I'll be asking
Yes, sir.
many such questions, some silly, some not so silly. All right. So very first question for this first session, the question is fairly straightforward. Which of the following is correct in terms of their resistivity? Okay, so resistivity is a property which I hope um, most of, if not most of you would have already about it. It's usually denoted by the symbol rho, right? And we have seen this in our high school or school level physics, that R equal to rho L by A, where L is the length of this conductor, this is the length L, and this is the cross section area A, and the current is flowing in some this direction, and we have applied a voltage like this. All right, so rho is a material property. You must have heard about these words, intrinsic properties and extrinsic properties. So rho is an intrinsic property, resistivity, right? So for every material, it's intrinsic. It means you can change the size, right? Resistors depend on L and A. So if you change the length, resistance will change. It's not so with resistivity. It's constant irrespective of the size of the material. Okay, so here we have given three classes of materials. One is insulator, second is semiconductor, third is metal, and we need to arrange them in the order of their resistivities. Okay, so let's do that. But first, let me ask you, what makes a material metal or insulator? So now you have to give me at least 3 points of each, and please answer me. What makes a material metal? Please respond. I'm waiting. You can write also if you don't feel comfortable. Anyone? What makes a material metal? Okay. Overlapped band gap. Yes, that is correct. Okay, so before that, I want you to recall your school level chemistry, your 10th, 8th, 10th, 12th, because I have recently had the privilege of reading the NCRTs, and I know that these things are talked about. That what is a specific, what are the specific, what is a metallic property? So I need you to answer that. Overlap band gap is correct. It's not that it's not correct. I want you to go to a level in which a 10th standard student can understand. Anyone? Or insulator for that matter. That's fine. How will you test whether the material is metal or insulator or semiconductor? It's a very simple question. I've given you a black box. I need you to tell me whether it's metal or insulator. How would you check that?
Sir, when I electron can flow.
Okay. One second. Please, just one by one. So Anuj.
Yes, sir. Sir, when I electron can flow in the material, this is the conductor.
Okay, so it's a conductor. Very good. Someone else was also speaking. So, okay, conductivity one's option. Very good. Conductivity is correct. Yes. Any other? Someone else also?
Sir,
Yeah.
the free electrons.
Free electrons. Okay, so now there I have to write it down. So free electrons. One is overlapped band gap. Okay, and there was one more, that was conductivity. Okay, so you mean to say metals have free electrons, and this was says metal has, so this is the table for metals. And conductivity. So conductivity high or low or intermediate?
So high.
High. Okay, so let me say high conductivity. All right, any other thing? What about insulators? So I am guessing insulators will be the inverse of that, right? No free electrons. We'll come to this term free. What does it even mean? Okay, so what happens with the band gap insulators? I am writing no overlap.
So the band gap is infinite?
Band gap is infinite. Okay, so let me just...
So band gap is large.
We'll come to that. Fortunately, we have some slides. We have some discussion today on band gap itself. This will be a good... So we'll end on the band gap. So let me write large. It's actually not infinite, but yeah, large band gap. So we'll also define what do we mean by large. Is 1 electron volt large? Is 4 electron? Okay, it's usually measured in electron volts. Okay, we'll see that. Conductivity, I'll say low. Okay, right. So as I was telling you, I was reading in class, NCRT textbooks from 8th or 10th standard. So there they had one very specific property. It was that it was shiny or reflective, right? And they have given the examples of gold, Au, aluminum, and so on. All right. So this I find intriguing. All right. So they have shiny or reflective, right? And then they said that insulators are usually dull in color. They had given examples of wood. Plastic was also there, right? Has anyone heard of diamond? Come on.
Yes, sir.
Yes. Is diamond a metal? Okay. Is diamond shiny or reflective? Whatever, if you have seen.
Yes, sir.
It's shiny.
Okay. So it should be a metal, right?
No, sir.
Why?
No, sir. Sir, it is an carbon compound.
Okay. So are you saying that all carbon compounds are are insulators? Is that what you are saying?
No, sir. No, sir.
No.
No, sir.
Okay. So let me just say, since you brought a very good point. Graphite, for instance, is not metal. I understand that graphite is not a metal in the purest sense, but it is conductive. It's a carbon compound, sheets of carbon, right? Diamond is also a carbon compound. These are allotropes, if you can recall. These are allotropes. Diamond is an insulator. Some people call it semiconductor, but let's forget about semiconductors. Diamond is an insulator. So there must be some property, right, which is shiny or reflective will not work. This definition of school level NCERT does not work. Okay, so this definition is not of relevance to us. What is of relevance is someone pointed out the conductivity, and conductivity in turn, what causes conductivity? One of the reasons is
Bandgap.
sorry. Go ahead.
Bandgap.
Yes, that's what I was saying. So conductivity, which was mentioned. So these two things result in conductivity. How, we'll see in the future lectures. That's not a topic for now. But what does happen is that these things, presence of free electrons and overlapping band gap, they cause a rise in conductivity. All right. So that answers are this question partially. We can keep on discussing it for ends, and there'll be no end to this. But let's move ahead with this understanding that we focus on conductivity. Okay. Then the next question is, what is a semiconductor? You have told me what is a conductor. Okay. First of all, metal, these are also known as conductors. But you should be very cautious when you are talking about conductors. We mean electrical conductors. There is also one called thermal conductivity. Electrical conductivity means the ability of a material to transport electrons. That's electrical conductivity. Thermal conductivity, the ability of a material to transport heat. That's thermal conductivity. So here we are talking about electrical conductors. When I mean conductors, I mean electrical conductors. For instance, diamond is a very good thermal conductor, but not so good electrical conductor. So our simplistic understanding of high school chemistry or physics just breaks down at as you learn more about the materials. Okay, fine. So what is a semiconductor? Now tell me this. We have talked about that we know it has to do something with conductivity, right? Because so you need to tell me that. Forget about this. Tell me, what do you know about semiconductors? What makes a material semiconductor? The question is simple again. Go ahead. Because I have been receiving some very good responses of metals and insulators. Go ahead.
So bandgap is small enough that electrons can cross it when heated. When the metal semiconductor is heated.
Okay. Small enough band gap for electrons to be what? Sent somewhere? I don't know where. Let's see.
Sir, in the conduction band.
Yeah, we have not talked yet about conduction band, right? That's what I'm saying. Your answers are correct. I treat me as if I'm a 16-year-old young boy. Okay, I'm double that age, but treat me like that. Okay, someone said he said both the characters. Both the characters. That's interesting. Both character of metal and non-metal. So let's talk about this property a bit more, and let's see if there are any other comments. Between conductors and insulators. Okay, so second and third point are, it says between metal and semiconductor. Metal and non-metal. All right. Okay, non-metal, by non-metal I mean insulator. Okay, so just I'm using these words interchangeably. They do not necessarily mean the same, so please take that in mind. But since I'm talking about only electrical nature, so hence I can use them interchangeably. Okay, so let's talk about between 2 and 3. So one person said they have both the characters of metal and non-metal, and other person said it's between metals and non-metals or insulators. So which one of them is more correct? You have to answer again, not me.
So second one.
Okay, second one. Okay, so he's saying second one is correct.
No, no, sir. The third point, right?
Okay, so let me cross this. And this is correct. Okay, so what, when you say between metal and insulators, which property are we talking about? That it's between
So
metal
the
and
conductivity
conductivity, yeah. Okay,
and band gap.
and band gap. Okay, let's just keep, okay, you can keep speaking about band gap, it's fine. I'll link this this discussion to band gap towards the end of a session, so that it will complete the whole picture. Valency, okay, very good. This is an interesting point. Valency, okay, let me recall valency. Valency is, I think, the number of electrons you need to gain, you need to lose or gain in order to achieve the noble gas configuration, if I'm not mistaken. So for instance, sodium will become sodium plus and lose, so it will become 1 electron, so hence valency of 1. That's what I recall, valency of 1. Similarly, chlorine will gain 1 electron, sorry, so it will be plus electron on this side, not here. This also has valency of 1. Okay, so now you have to tell me how is valency related to semiconductor behavior. Someone has to tell me this, because this point has been brought up. Polarity of carriers is both positive and negative. Okay, so what do you mean by polarity of carriers? Oh, polarity I understand. I know only one polarity. Polarity of carriers. Okay, by the carriers here we mean charge carriers. Okay, it can be positive or negative. Okay, negative I am assuming it's electron. What's a positive charge? What's a positive carrier?
So a hole or lack of electrons.
Lack of electrons. So we'll talk a bit more about in the future lectures, but it's correct. A hole. You will keep hearing this term. Hole is literally a hole in this case, because there's an absence of electrons. So if you recall, there's a nucleus and there are orbitals, right? 1s, 2s, 2p and so on. Let's say there are two electrons here and 2 electrons here. If I somehow get rid of this electron, there's literally a hole here, right? That's why these are called holes, and these are so Na plus will lose an electron, so hence it becomes positive. So holes are positively charged for that reason. Okay, polarity of carriers, it has both the polarity of carriers. That is correct to a certain extent. Yes, semiconductors can have both of them. Not necessarily. There are some semiconductors which have only one type of carrier. So for instance, one of my colleagues work on it's the material I'm forgetting. They have very low amount of positive holes. They only have the electrons. Okay, so this is true to a certain extent, but not always. Okay, so right, very good answers here. So we'll talk about this point number 1 sometime later. Small enough band gap for electrons to be sent. Sent where? I'm still waiting for this answer.
Conduction band.
Okay, so we are again back to bands. Okay, to be sent to conduction band. Very good. So they'll be sent somewhere, right? And maybe they'll contribute to current. We'll see how. Point valency. These two things we have talked about. Between metal and insulator we have seen. Valency. Okay, in a certain extent it plays a role. For instance, if you've seen the lectures, there are group 4 elements like carbon and silicon and germanium. Carbon is not a semiconductor. Carbon is a non-metal, but silicon and germanium are. So valency does. I'll not say valency dictates the semiconductor behavior, but it's linked somehow. Not necessarily that it will cause. It's not a reason for causation, but there is some linkage. For instance, GaN. This is a semiconductor. Gallium is group 3. Nitrogen is group 5. Right. So 3 and 5 you can say average is 4. And say that, but for that matter you can say NaCl also, but that doesn't make it semiconductor. NaCl in fact in its aqueous form or molten form is a very good conductor of electricity. So we have to be very careful when we link it to valency. All right, this The key takeaway from the last slide, as we see it from the first itself, is conductivity itself. So here you can see on the left side in blue region you have the insulator. So conductivity you can see, and this is from your lecture notes. Conductivity is measured in Siemens per centimeter, right? Siemens is basically your 1 over rho, right? 1 over rho. Rho is your unit for resistance. So this is conductivity, and you can see conductivity is very low for insulators like quartz. This is essentially silicon dioxide. Glass is also somewhat similar, silicon dioxide. Diamond, you know, is carbon. Rubber, I don't know the formula, but it's a carbon base. That's the only thing I know. Germanium and silicon, these are a group 4, which we have seen in the last slide. Gallium arsenide, gallium is 3, arsenic is 5. So this is a 3-5 semiconductor. Why 3-5? Gallium is group 3 and arsenic is group 5. Hence, this semiconductor is 3-5. Cadmium sulfide, cadmium is I think group 2 and sulfur is group 6. So this is a group 6 semiconductor. Here you can again see this thing 4, you take this average, comes out to be 4. Valency has some correlation, that's what I'm saying, but carbon also has 4 valency. It's not, usually carbon compounds are not semiconductors. And here are metals, so which are good conductors of electricity. One key thing you should note that these are dots here. This means their value is fixed. You cannot change them. Here it's a line. This means the most beautiful part about a semiconductor is that you can change its conductivity according to your need. Silver cannot be changed. It's around 10 to the power 8 Siemens per centimeter, right? Aluminum cannot be changed, around 10 to the 7. But you can change the silicon. It can range from 10 to the power minus 5 Siemens per centimeter to 10 to the 3. How we do that, we'll see in the later slides, but there's a hint, it's doping. We can dope them. We can add some impurities in order to change their conductivity. That's a very good control that as material scientists have given to device engineers, right? This means you can change as per your wish how much current you want, right? You can change that according to your wish, which is not possible in case of metals or insulators. That's the best property of a semiconductor. All right, so in terms of resistivity, okay, so we talked about that conductivity of metal is greater than conductivity of semiconductor is greater than conductivity of insulator, and rho is inverse of conductivity. Okay, so I'll just flip the signs. So rho of metal is less than rho of semiconductor is less than rho of insulator. So insulator is greater than semiconductor is greater than metal. So this is the correct option. All right, any comments or questions for this problem that we had talked about? This was I know we took a this is a very simple problem and we took around 20 minutes for that. And that's fine because I need you to warm up and this needs to be interactive. Some other problems we'll talk about will not take so much of time. So if you have any comments or questions, please go ahead. All right, so that's good. Just the takeaway from this problem is that during this course we mainly focus on electrical properties, and of which resistivity or its inverse conductivity is the most important property that we care about. Okay, so in fact all the research just goes on how to improve the current carrying capacity of a device. All right, so now as the course suggests, introduction to semiconductor devices. Semiconductor devices usually now are now the device, for instance, the device I showed you, the picture of the device that I have made, that's in a few microns. Even in that there's a structure which I have made of 200 nanometers. Okay, so then this is in a lab. In the industry, if you go, the Intel and the Samsung, they are making features on your device which are less than 10 nanometers. Okay, and in that region classical mechanics does not play that important role. It plays, but it's small as compared to what is role is being played by quantum mechanics, which comes in only when we talk about the something called a De-Broglie wavelength. We'll talk a bit about this here, De-Broglie wavelength. Okay, let's just see this problem. The question says the wavelength of an electron in nanometers that has a velocity of 10 to the 3 meter per second is. So we need to find the wavelength of an electron. right? This is somewhat confusing because for a long period of time it was understood that waves and particles are two different entities. They have no relation to each other, they're independent of each other. For instance, water, when you drop a rock in a pond, in a calm pond, the ripples, they travel out. So we know there's a wavelength, there is a frequency to the waves, to the water waves that are traveling. That's fine, that's a property. And if we throw a ball at a wall, or we, or when on a sports person hits a ball with their racket or a bat, so we know that it's hitting at this angle with this much force, the impulse has been provided, and this is the final velocity given the initial velocity. That's a particle. We exactly know what is the, at what point of time, what is the velocity. In cricket we have this Hawkeye technology which tells that whether the ball is going to hit the stumps or not. It's a particle, we know everything about it. Then some people said that okay, it's not true, everything is dual, everything is a wave as well as a particle. So what is a wave feature? One of the most characteristic feature of a wave is its wavelength, right? So in this case we are talking about an electron. Recall the problem says an electron, right? An electron, you must recall, is a subatomic particle, means it resides inside an atom, right? Can anybody tell me what is a typical size of an atom? Size of an atom, anyone? All right, let me put it in different matter, in a different perspective. So these are two atoms. What is this distance called typically? So this is atom 1, this is atom 2. What is this distance? It has a specific name to this. Okay, somebody responded. Okay, angstrom. Okay, you're talking about the range, I believe, of the size of an atom. Is it angstrom or even lower? Yeah. So okay, that's what I'm saying. Let's not talk about atom, because when we are, all the matter that's around us, it's composed of more than one atom. Very rarely you'll encounter, or even in semiconductor devices, it's what we call a lattice. So it's a periodic arrangement of 2D or 3D arrangement like this, something like this. So these are individual atoms. So difference between two consecutive atoms is what we known as lattice parameter or lattice constant. The distance between two consecutive atoms, okay, is called a lattice constant. This is usually in the range of angstrom, as someone suggested. Atoms are still much smaller, and nucleus even smaller. Nucleus in, I think, in what's that, femtometers, right? And so this is the distance between two, lattice constant, it's in angstroms, okay. And as I told you, so atom, the distance will be even smaller, atom size, right? Or let's say for the sake of discussion is comparable to angstrom. So when we are talking about an electron is residing somewhere inside an atom, not a free electron, it's bound by the nucleus, right? And we denote this, that we say that this atom, this electron, although we consider it to be a particle, it has a wavelength associated to it, which is called a De-Broglie wavelength. This we'll see why it comes. But we know that particle features momentum. I talked about a cricket ball, right? When you're hitting, you know its position, its momentum, and if it's whether traveling in an x direction, y direction, what you know everything about it, right? And this is, and energy is one more characteristic of it. So this is the relation which you typically see, equal to p square over 2m. So p is your mv, m is your mass, so p we typically denote it as mv. I'm ignoring the potential energy here, okay. So hence the energy, total energy will come out to be p, mechanical energy come out to be p square over 2m. P here again is the momentum itself, and hence these two things are related. These are not independent of each other. That's what was hypothesized, and that's what we have been it's demonstrated over and over again when we talk about some atomic particles. This is what we have found to be truthful. As I told you, when does quantum mechanics kick in? Okay, when does quantum mechanics kick in? If you see your lecture slides, it says quantum mechanics kick in when we approach the De-Broglie wavelength regime. So De-Broglie wavelength is an important thing to remember, that only when you encounter these distances, then only you will encounter the quantum mechanical effects. Then only they become significant. It's not that they're absent. Even in macroscopic regime, when a ball is being hit by a bat or a racket, quantum mechanical effects are still present, but they are so overwhelmed that their effect is not seen by us, That's the thing. Okay, so let's simply do this lambda b equal to h by p. So we know lambda b is equal to h over p. H is Planck's constant. I always forget its value. Can someone tell me what's the value of Planck's constant? 6.626
10 raised to the power minus 34.
units. That's important. Units. Okay. I have encountered this problem myself. I have lost marks due to this. Remember, E equal to h nu. E is the energy of the wave. H is the Planck's constant. Nu is your frequency, right? So I know energy is joules. Joules equal to the units of h, whatever they will be, times nu. Nu is frequency, so that's 1 over time, 1 over seconds. So h units will come out to be joule seconds. This is joule seconds. All right. Over p. P is nothing but your momentum, right? And momentum is mass times velocity. So this is nu, this is frequency, this is velocity v. Let's do this. 6.626 10 to the power minus 34. Mass, I remember 9.1 10 to the power minus 31 kg. Remember, everything I am doing in SI units. Please be careful when you are attempting these problems, either here or your semester exams or internal and whatnot. This can be very disastrous even in real life if you make this mistake. I forget, NASA sent some mission, I don't know to which planet, but they made this error of they had a problem conversion of units. So in US they use they don't use SI units, they use something is called imperial units, so they use pounds. Some good fellow had put in that the weight in terms of kgs, and they forgot to convert into pounds, and the whole mission failed. A lot of money was and reputation was burnt to no success, right? This is kg. V is 10 to the power 3 meters per second. This is also SI units, so I'll put it as is. Everything is in SI. Now I just need to calculate. So this will turn out to be 10 to the power minus 6, 6.6 over 9.1 into 10 to the power minus 6. Let me get my calculator. This will be 6.6 over 9.1. So this is coming out to be 0.725 into 10 to the power minus 6 SI units, because everything is running in SI units here. So I'm asked for in nanometers. So nanometers 10 to the power minus 9 meters. So that will be 725 into 10 to the power minus 9 meters. 10 to the power minus 9 meters is nothing but your nanometers. So it comes out to be 725 nanometers. So this is the correct option, this one. So let me just repeat what we did here. So okay, so what does this mean? This means that if an electron is traveling with this much velocity, if you encounter any distances around 725 nanometers or lower, that means quantum mechanical effects will come into play, right? So that means you have to apply your Schrodinger equations, your Heisenberg uncertainty principle, and all those things will come into picture. You cannot ignore the quantum mechanical effects anymore. All right, that's what this means. That's the significance of this number, 725 nanometers. And you can clearly see, if I increase the speed, let's say I have 10 to the power 5, for instance, the work that I do in my research work, there I have velocity of 10 to the power 5 meter per second of electrons, right? So if I increase the denominator, right, so there this 725 nanometers will become 7.25 nanometers, right? So even for myself, I do not see quantum mechanical effects to that extent. They are present, but only in certain regions I see them, right? So that's why this is a very important term. Whatever the velocity or the momentum in this case is closely related to De-Broglie wavelength, which again determines when will quantum mechanical effects will become prominent, and you have to take that into your consideration for your simulations when you're working on actual devices, right? So okay, I should stop here. Any comments or questions regarding the De-Broglie wavelength or whatever analysis we did here? Okay, I understand the problems are simple.
No, sir.
Okay, let's go ahead for third problem that we have. So it says that the relation between the momentum of a one electron volts electron. So we need to find the relation between the momentum of electron, which is given here by Pe, and momentum of photon given by Ph. They both have the same energy, so we need to find the relation between their momentum. So I can see that the energy of electrons has been given equal to energy of photon, which is given to be 1 eV, and I need to find what is the relation between their respective momenta. Okay, so this is the problem statement for me. This has been given, right? So clearly, as we have just seen that the usually see again. Okay, let me go ahead with the slides itself. So what's a photon? What is photon wavelength? So this question talks about that. Question talks about the energy, right? Energy of a photon. So there's a close relation. We just saw that E equal to h nu. I talked about that, right? This is nothing but a photon. The energy of a photon, energy of light. Okay, so what's the wavelength of a photon? So we know photon is a quantum of light. So light, if you recall, is a continuous stream of photons, and each of those photons has equal energy and a specific energy, right? And that's why a photon is called a quantum of light. And wavelength is a wave property, and this is typically straightforward, that we know light, that it's a wave. It's an electromagnetic wave with its E and B, the electric field. And so if you recall something like this, so if this is your E and your B can be in this direction, and then your wave will be propagating out of the plane. So this is E B, there's a E cross B. There are many some vector algebra involved, but essentially it's electromagnetic wave, transverse electromagnetic wave. So wavelength is a wave property of light, right? And we know E equal to h nu. E is the energy of a photon, of one single photon. Nu is the frequency of that photon. Okay, and I also know that nu equal to c by lambda. How do I see? Lambda is the wavelength. How do I get to that? So c is the speed of light, right? Is you can say the wavelength by time period. Very simply, speed is nothing but the time taken by the wave to travel one wavelength. So that's how this comes out to be, lambda by t. T is nothing but 1 by mu, so lambda into nu, hence this comes. Okay, so I rearrange the terms. E by c is nothing but h by lambda. And what is E by c? E by c in case of a photon is nothing but a momentum. And notice this is the same formula that we have seen before for De-Broglie wavelength, right? This is the same formula. Lambda we saw there was h by p. Lambda electron we had calculated, h by pe, right? Okay, I'll pause here, and I want you to recall one of the important effects, if you can tell me that, of a photon. Somebody tell me. It's a very important effect that we talk about when we talk about photons.
Photoelectric effect.
Very good. What is that?
Sir, on acquiring sufficient amount of energy, the electron ejects out of a metal.
All right, let's break it down. You said photo electric effect, right?
Yes, sir.
What is the cause here? What is the effect? Tell me the effect. Whatever you're saying, just repeat that for again so that I can write.
Sir, from any metal surface, if we provide sufficient amount of energy or the photon, the electron absorbs energy from the photon and rises to the higher energy state.
Okay, so I'll say that the end result is increase in electron energy.
Yes, sir.
Okay, is the electron ejected out of the surface?
Not completely ejected. It comes in the highest state, but also returns back after the transition time period.
Okay, so this is saying this is the result. And what is the cause? Cause he's saying is a photon, which is correct. That's why the name suggests photoelectric effect. There are many other effects. There are thermoelectric effects also. In that you provide energy through heat, in order to excite an electron. So here the result is increase in electronic energy, and there is something also called a work function. So the metal, so the electron, as you talked about, electron is usually bound to a nucleus, it's not free, right? But if it gains sufficient energy, in this case due to the high energy photon, and this is, by the way, this is the energy of a photon, so what's going to happen is that some of part of that energy will be used by electron to break its bond with the nucleus. So there's an energy, potential energy between the electron and the nucleus. So if you provide a high enough energy, in this case due to a photon, it can break that bond and it will become a free electron, since it has now now it has become free of all these worldly bonds. It's become a saint. And if you provide sufficient more energy, which is called a work function, it can even come out of your surface, right? So that's the photoelectric effect, and this is one of the very important effects of a photon, where so in this case, remember, photon is a wave, right? Electron, but we knew, was a particle, right? But here a wave and a particle are interacting. This is again one of the demonstrations which establish that there's a wave particle duality that's existing. These are not two separate entities, waves and particles. Everything is a wave and everything is a particle, right? All right, so we know in the case of a photon, the momentum is given by E by C. You can see from this formula. Okay, so what I'll do is that I'll first calculate the momentum of a photon, right? So let's do P of photon. We just saw it is E by C, right? The value of E is given to be 1 electron volt, and the value of C is 3 into 10 to the 8 approximately meters per second. Now note that the units above here, no, it's SI, okay. So let me convert it in, do I need to convert? Okay, let me just also calculate the momentum of the electron here. So it's going to be okay, so now remember that E equal to P square by 2m. Just hold on a second, let me do this. Yeah, so E, energy of electron, is nothing but P square by 2m, right? So what will be the momentum? Momentum will come out to be simply twice the mass of energy, so a mass of electron times the electronic energy. That's what will come to, okay. And so let's just put the values. The mass is 9.1 10 to the power minus 31. The energy is 1 eV, so everything will have to be in SI units. So eV will turn out to be 1.6 10 to the power minus 19 volts, which is SI units. So I need not worry about it. So let me just calculate this value. Just hold on a second. 3.2 into 9.1, square root of that, it's coming out to be 5.4 into, that's minus 50 meters per second. All right, and let me calculate this value. This is 1.6 10 to the power minus 19 volts. I'm just replacing the value of E here, which is the electronic charge, which I did the same here. This was volts, then divide by 3 into 10 to the power 8 meters per second. So that will turn out to be 1.6 by 3. That's coming out to be around 5.3. One second, so sorry, it's 0.53 into 10 to the power minus 27. So that's coming out to be 5.3 into 10 to the power minus 28 meters per second. You can now clearly see that despite having the same energy, an electron has much more momentum. It's evident. In fact, 3 orders more. Minus 25 is much higher than minus 28, right? So we notice that this is the correct option. Momentum of electron is much greater than momentum of photon. And this is one thing that we so from the numerical perspective we have solved it. What do we gain from this? So we notice that even though they have the, so this is a thing which keeps on coming. So even so, a 1 electron volt electron, an electron with the energy of same energy as a photon, will have much higher momentum. So when you want to knock something out of a material, right? You need high momentum, not just high energy. You also need high momentum because you want to break the bond, right? So for sometimes it's just mechanical force, or in this case momentum, which will help you achieve that. We'll see that in the coming lectures, something called impact ionization, and all those effects will come into play, and there the momentum will play a role. Okay, so just keep that in mind. We'll revisit this again. So for now this problem is complete. Any comments or questions regarding the photon or an electron and the De-Broglie wavelength? I'll wait for your comments, and then we'll go ahead for next set of problems. All right. Okay, so this is again a very classical, not classical, quantum mechanical problem. Heisenberg uncertainty principle is given by. So if you I understand that many of you are not aware about this, or may not want to understand about the quantum mechanical world or the equations that are driven. But there are few things in that quantum, like for instance in Newton's laws, there are 3 Newton's laws that you have learnt about. In thermodynamics, you know, zeroth law, first law, second law, and so on, right? Similarly, there are some postulates of quantum mechanics. There are some very basic facts that we keep on reiterating, that the quantum mechanical regime keeps giving it to us. Heisenberg uncertainty principle is one of them. So the question asks which one of the following statements is correct regarding that. So for that, we first need to understand that one very basic difference between quantum mechanical and the classical mechanics is that in classical mechanics, I have talked about deterministic means you know x, what's the position, y and z also, but let's talk only about one dimension. You know momentum, you know force, right? You know energy. All these things are known precisely at the same point of time, right? All these things are precisely known. There's no probability. Probability is 1. When you know your ball is at this location, the ball is at that location. There's no if and but. We know that. Quantum mechanical does not run on deterministic, it runs on probability. And hence, since it runs on probability, there's an uncertainty involved. Now, uncertainty, we know it in different words. You must have heard about this word, standard deviation.
Yes, sir.
Can anyone tell me what is standard deviation? Simple terms. Not again, you have to talk to a person who's in a 10 standard or 8 standard, that manner.
The variation in a value in terms of its original value.
That's a very good definition. In fact, let me elaborate on this. So let's say I have there's an x some variable. So let's say what's the temperature right now? Okay, let's do this way. So what's the temperature at 3 p.m. in Bangalore, where I'm sitting? So today I measured, I got the temperature T1. Tomorrow I measure, I get T2, and I keep on doing this for the whole month of July. So I get 31 readings, T1 to T31, right? But as you can predict, all the temperature will not be the same. Sometimes it's hot, somewhere it's raining, so on. So there will be an average to this value. So let's call this their averages T average, right? And then each of these values will differ from this T average. It's highly likely that it differs. How do we measure them? We measure them through some variable called standard deviation, right? How much it's deviating. Can anyone now tell me the formula? This is the basic understanding. The formula for standard deviation. There's one more term related to standard deviation. I'm forgetting that. Standard
Variance.
Yeah, variance. Correct. Yes, variance. Right. So these one is the square root. There's no much difference, right? Which one is the square root? They are related somehow.
So variance is the square root.
So I can write variance is square root of standard deviation. All right. This is also known as uncertainty in quantum mechanics. This is exactly mathematically, this is the same thing. We are talking about probability, right? So we don't know whether particle is at position 1 or position 2, whether momentum is P1, P2, P3. So we take multiple readings, just like I did with this temperature, right? Just like I did with this temperature, and I take an average, which is called the mean, and then I take a standard deviation, which is known as the uncertainty, right? And uncertainty is, if you see here, this is the uncertainty in momentum, position. This is certainty in position. This is uncertainty in momentum. As I've been saying that this is probabilistic regime. We don't know where we are. We don't know what's the momentum. Hence, actually there is a derivation involved. It's a long derivation. I'm not going through that. We are not going to go because it involves some quantum mechanics, complex conjugates and so on. It will be a bit overburdening for this session. Quantum mechanics class, it's fine. If you are interested, you can just get back to me. We can talk about it. I can share the link where you can read more about it. But this is essentially the relation that is. So you can see if you know the so what's the takeaway? What do I understand of all this talking? It's very simple. Delta x, if you know x precisely, correct, your delta p will be infinity. So if you know your position correctly, you don't know the momentum at all. If you know the momentum, you don't know the position, which is not the case in classical mechanics, as I'm telling you. The cricket ball is coming, we exactly know this is the position. The position is the ball has just hit the bat with so much momentum. We know everything about it in classical mechanics, not so much in quantum mechanics. Hence, this is a very famous uncertainty principle. It has two flavors actually, right? This is the x and p, and this is in terms of E and T. Again, E is your energy, and T is your time. So if you know the energy precisely, you don't know at what time it was measured. And if you know the exact time, you don't know the energy. There's always a trade-off that is involved. That's what I mean to say. Everything comes at a cost. If you want to know the energy, you have to sacrifice a lot of time. So these are the things you should keep into account, right? Okay, just to summarize, so this is a fairly straightforward problem. The answer you can just see h cut by 2. Okay, one more thing. This is h cut. This is also known as h cut or h cross. I should have said so. This is nothing but h over 2 pi. And similarly, there's another entity k, which is 2 pi by lambda. This is called a wave vector. Okay, so just remember that. And why are they coming about that, we'll talk. So first of all, the option would be this option, and I was saying h cut was h over 2 pi, and there's something called k, which is 2 pi by lambda. This is called also known as the wave vector. This is just an entity related to lambda. So we saw that p equal to h by lambda. So I can write it as h by 2 pi multiply and divide by 2 pi by lambda. This is nothing but your h cut. This is nothing but your k. This is also one of the very famous relations in quantum mechanics. P equal to h cut k. P is your momentum. This is your Planck's constant, also known as reduced Planck's constant, because it's divided by 2 pi. This is nothing but your wave vector. So sometimes you will see, we also see in this class that sometimes you need to plot against k. Fourier transform, there's so many terms are involved, but just keep this relation in mind. That's all. All right, anything up to this point of time, because now we'll just go a bit deeper, not too much, in particle in a box problem, that is the potential wells and Schrodinger equation and so on. So I'll pause a bit here. Till now we have just talked about some very basic things of like De-Broglie wavelength and the Heisenberg uncertainty principle, which are very basic terms or concepts in quantum mechanics. So if you have any comments or doubts, you can speak right now, or you can email me as I've been telling you. It's fine too, whatever you prefer.
Hello, sir.
Yeah, go ahead.
Can you please repeat the statement on when photon behaves as a wave-like behavior and electron behaves as a particle-like behavior? When energy is electron has more momentum, it has a ability to jump out of the shell. So that part has not been clear. Can you please repeat it?
Okay, so what I was saying was that okay, so first of all, a photon, what we typically associate photon is light, right? And light is a wave that has been traditionally known, right? An electron, which we associate to be a particle, that's what a traditional understanding was, right? So I was commenting on that nothing is purely wave or purely particle. Each entity has duality involved in that. So light will also have some material properties, particle properties, and this is a, so you can understand that a ball will only interact with a ball. Understand, the ball is a particle, right? So a ball will collide with a ball, and then only you can see some effects. Here what we were seeing is that when we hit light on a material, we saw some electrons coming. Till that point of time, in photoelectric effect, we had understood that photon, which is light, is nothing but a wave. The electron is a particle. So how are they interacting? They said that light is, you can assume light to be consisting of something called particles known as photon. Just think that a lot of balls are falling on a material. Each ball is called a photon. It's a particle, right? And based on that, they evolved these form. This is a very simple formula. E equal to h nu. We know the energy, and from this we consider the momentum, which is typically a particle property. Okay, we associate with to a wave also. That's the difference. Okay, and here what I was saying is that in this problem we had the photon and electron both had the same energy, in this case 1 eV, right? But we saw that electron had much more momentum. All right, what happens is that where does that come into handy? It comes into handy when you want to knock something out. So you can understand that you have a wall, right, and you want to just break one brick in that, not the whole wall. You want to punch a hole. What you want is you want large momentum, because if you recall a classical mechanics, that your momentum and impulse have a relation, and force, so on, right? So when you have a larger momentum, you have a higher chance of knocking it out. That's what I meant here. Despite having the same energy is important. I'm not saying energy is not important, but apart from energy, momentum is also important, especially when you're talking about collision problems, which we'll see in some later part of this course when we talk about ionization and impact ionization. All right, does that answer your question?
Yes, sir. That was clear, sir. Thanks a lot, sir.
Okay, you're welcome. Okay, that's Heisenberg, and now we come to the problems. This was covered in class. I mean, just the problems are linked to that. So in the class you must have read about potential wells, right? So here this is a problem related to that. So in this says, consider a particle in a 1D potential box of width L. I'll explain what that means. E1 is the energy of the ground state, and En is the energy of the state with quantum number n. What is the ratio of energy when the particle makes a transition from n equal to 3 to ground state? So let me just draw this. This is a particle in a box. So this is a box. Here it's infinite energy. So particle is forever confined to this space. Unfortunately, it cannot leave. Just a second. Yeah, it cannot leave. So this is its ground state energy. Okay, let's call this E1. This is E2. This is E3. And this is somewhere will be here E5. So particle can move between these states provided someone provides it energy. As someone was talking about, someone like photon can provide energy, anything can provide energy, or by heat. So what's happening is that is the ratio of energy emitted when the particle makes a transition from n equal to 3 to ground state. So let's say what is the energy emitted. So delta E31. Why E31? Because I want to go from E3 to E1, from this state to this state. This is my delta E31. Oh, Sagar, it's not always rectangular in shape. I'll come to that. This is just because it's easier to understand. The mathematics is easier. So when you are introducing the concepts to someone who's new to this field, we talk about this kind of a potential. It's not always rectangular. We'll see this class itself, right? And this is E5 minus E1. All right. So the question is, what is the ratio of delta E31 over delta E51? This is what we are required to find. All right. Just a sec. Just a second. Okay. All right. So as I was saying, it's not, quantum mechanics is not deterministic or probabilistic. And how is this probability determined? This is denoted by something called something called a wave function, which you call it psi. This is the symbol for that. and this is the equation which I mean it's simplified, but it might look big, but it's one of these. It's called time independent Schrodinger equation. You do not see any time term in this. Remember I talked about E and T, and I thought delta E into delta T is greater than h cut by 2. So there's one more expression which has time also involved, but here we are not considered about this. E is the energy, psi is a wave function, x is the position, v is the potential. So you can see this is a differential equation only in x, right? That's the only variable that we have here, and we already answered this question. So when is quantum mechanics valid? Can you now tell me? I have repeated this at least twice or thrice, and so did Professor Naresh in his lectures.
Sir, when a particle approaches De-Broglie wavelength.
Yeah, De-Broglie wavelength. And please remember that, so this is when we approach the lambda b, and please remember that this is dependent on momentum. It's a function of momentum. So when you change the momentum, this will change. This is very important. Sometimes due to various reasons an electron might get excited, it gains momentum, then the De-Broglie wavelength will change. So our whole analysis will also change, right? Okay, so this is the expression that we saw, and the question talks about 1D infinite potential well. This is also known as a box, famously known as particle in a box. And this is your box, as Saga just pointed out. Why always rectangular? Here we just be patient. Here it's rectangular. All right. So what we have here from less than 0, for x less than 0, the barrier is infinite. This means you cannot escape here. You cannot go here. Similarly, for x greater than L, barrier is again infinite. You cannot go here. So only the particle which is somewhere here, say this, it's confined to stay between 0 and L, right? And where it is, we denote it by psi x, where it is, right? So that's straightforward. How to solve it, I'm not going to solve it, but we can just say that. So we can say that what is psi x? Psi x equal to 0 for x less than 0 and x greater than L. This is we know. And second thing, we know that Vx equal to 0. So this means we only need to know between 0 and L, right? So we don't know this for 0 less than x less than L. You can say equality here. Vx equal to 0 for 0 less than equal to x less than equal to L. So if you solve this expression only for 0 less than equal to x less than equal to L, Vx will become 0. So the expression will become h cut square by 2m del square by del x square psi x equal to E of psi x, right? Now you can see that this is the only variable that we have. It's also dependent on E. Okay, you can go through your lecture notes, and what you will come out with is that the answer comes out to be something like this: n square h square. Can someone just tell me what's the expression for energy? Anyone?
N square h square pi square upon 2m L square.
This one?
Yes, sir.
Okay, so let's go ahead. I'm assuming this is the correct formula. Doubt because there are two formula. Some h cut is
so
also.
it's h cut square, not h square. It's h cut.
This or this pi
Yes,
square?
n square pi square h cut square divided by 2ml square.
Okay, fine.
Yes.
Okay, so this is the expression. Again, I'm not deriving this. This is in your lecture notes. That's not a problem. But I'm trying to see how to approach this problem. That's our aim here. So as I told you, this is the well now. There'll always be some E1, and this was E3, and this was E5, and it goes up to infinity. I'm not bothered about that. So my only aim is when this goes from here to here, I'll find out this energy, and again I'll also find out the energy when it goes from here to here. That's a mechanical problem. Let's just first solve the problem, and then I can tell you that what is to be learned from this, right? Just a second. Yeah. Okay, so let's calculate delta E31. That will be E3 minus E1. So that will be 3 square h cut square pi square over ml square. That was the formula, right? 2ml square minus 1 square h cut square pi square upon 2 ml square. So I am taking everything common, so h cut square pi square over 2 ml square common, so that will be 9 minus 1, come out to be 8 h cut square pi square over 2 ml square. So that's the first part, delta E 31 from here to here. Okay, let me change the color, let's take blue. So blue is my delta E 51. So delta E 51, again you put the formula here, so that will be 5 square minus 1 square, nothing else, everything else remains the same. That comes out to be 24 h cut square pi square over 2 ml square. This term is constant, that's why I was not worried about it when you told me the formula. I don't care about this for now. And we are required to find delta E 31 over delta E 51. That comes out to be 8 h cut square pi square over 2 ml square, the term in red, divided by the term in blue, which is 24 h cut square pi square 2 ml square, comes out to be 8 by 24, it comes out to be 1 by 3. Okay, this is our option. What does it mean? What do I gain from this knowledge? Right, this is fine, numerical I have worked out fine, I'll get my marks. What you notice is that it's not linear, which you can also see that it's n square involved, right? So what it means is that as n increases, n is the quantum number, that is somewhere it was written quantum number n, yeah, this means as n increases, the difference between two levels increases. You can see that it will be, so let's give it some units. It will be 1 unit, this will be 9 units, this will be 25 units, then there will be E7, that is 49 units. You can see the gap between two consecutive, this is 8 here, 16 here, 24 here, the gaps consecutively keeps on increasing. That's important. This means that if your n is low, if your L is low, if you want to deliberately increase your gap between two energy states, which we do in some, there are some application which you deliberately want E1 and E2 to be very spaced apart, which is very true for the work that I do, that's required for me, that E1 and E2 should be very much spaced apart. From that I have to make sure the L is small enough. Okay, there I have to deliberately make some material in such a manner that this is different, that there is a large space between them, or sometimes I want them close, right? So I'll increase my L, and you can see L, which is the length of this box, this particle in a box, let's say L is 1 centimeter, which is your macroscopic length, and you will see that all these levels will be so small because it's centimeter square, right? If you calculate these values, this will be very small, that you will not see them at discrete levels. You'll see them like this. When L equal to 1 centimeter, you will see something like this. They'll be so close together, you'll not be able to distinguish, and this is called a continuum. And this is in macroscopic. That's why I was saying in classical mechanics, macroscopic regime, you do not see quantum mechanical effect. This quantization means there is a gap between two consecutive levels. You will not see this in, you have never heard that the velocity cannot be, if the velocity is 1 meter per second, you never hear it cannot be 1.2 meter per second. You can see it can be everything. 1.001 is also possible if you can measure that. That's the difference. When you increase L, your delta E will become so small, it's irrelevant. It's as if every state is the same. That's the significance of this problem. That's your takeaway. Okay, I'll pause a bit here, and if you have any comments or questions, please speak. Just remember, you can memorize the expressions, that's fine. Like I could not have recalled the expression for this energy, but what you must understand is their dependence. They go as n square and they also go as L square. So for heavy particles like cricket ball, its mass is 10 grams, mass of electron is 9.1 10 to the power minus 31, and a ball is 10 grams, let's say 1 gram, so 10 to the power minus 3 kgs, right? You can clearly see the difference between E is 10 to the power 28 times. That's huge. That's why you don't see quantum mechanical effects. So all your energy will be so close together, you will not see a difference. You do not see that there is a gap in between them. All right. Okay. So now next problem is in a 1D potential well. particle with mass m and 0 energy. So energy has been given equal to 0, and this is the psi that's been given to us, a e to the power minus x square. We are required to find v0, that is the potential at x equal to 0. So what we do is that this is the expression that has been given to us, and we know E equal to 0, so this term vanishes. So I'm writing this expression, h cut square by 2m del square by del x square plus vx times psi x equal to 0. Okay, expression for psi is a e to the power minus x square. So let's do that, h cut square by 2m del square by del x square, multiplying psi x here, plus vx times psi x equal to 0. Remember, psi is a e to the power minus x square. So let's take the first derivative. So it will come out to be a exponential will remain the same. Then we take the derivative of the exponential, it will turn out minus x square is minus 2x. There's one more derivative after this, plus vx psi x equal to 0. I've just taken first derivative, now I'll take the second derivative, h cut square by 2m. A is a constant, so is 2. Let me do it again, sorry about it. Okay, so minus 2 and a I can take out, so it will become h cut square a by m, and it will be the derivative of this function. So that will be del by del x e to the power minus x square plus vx psi x equal to 0. Okay, so let me repeat this expression, h cut square a by m, and now I'll take the derivative of this. So I'll take first this is the a and b, two functions. First I'll take the derivative of a, so that will be 1 e to the power minus x square. Then I'll keep this term as it is and take the derivative of the second function, plus vx psi x equal to 0. Let's take e to the power minus x square common of it. This will come out to be 1 minus 2x square. Yeah, 1 minus 2x square plus vx psi x equal to 0. Now remember that we are required to find at v0. That means put x equal to 0 in this whole expression and we'll get our answer. So let's do that. So by m e to the power 0, 1 minus 2 times 0 plus v0 psi 0 equal to 0. So that will come out to be h cut square by m. This will turn out to be 1 plus v0 psi 0. Psi 0 is nothing but your a, because remember psi was a to the power minus x square. So from here you can get v0 equal to a will get cancelled, minus m by h cut square. You can cross multiply and we'll get this answer. Sorry, not the inverse. It will be minus h cut square by m. A and a will get cancelled, minus h cut square by m. Yeah, this is the option. So this is a very straightforward problem. It's just that you put the value of psi x, you know this Schrodinger equation, and you just take the double derivative of it, and finally, since we are required to find the v at x equal to 0, that's the hint was also given. Take the second derivative and we simply put it and we got minus h cut square by m. Any doubts? It's very straightforward. There's nothing to be learned from this problem per se, except that except the mathematics of it. That's it. So which I just demonstrated how to do it. Okay, now this is the last problem I think for wave functions for the particle in a box, right? And then we'll quickly jump to our band gap thing. Okay, so the question says there's a wave function that has been given, which is this. Now remember, till the time we were talking about the wave, the box which is starting from 0 to L. This is 0, this is L. This time the box is different. The box is from minus L by 2 to L by 2. I'll move this show this in the next slide in more detail. we have to find the correct B value. There's a hint given. B can be determined by using total probability of finding a particle that acts unity. So please understand that here it's still a particle. It's behaving like a wave, but it's still a particle, and the particle physically exists. We know electron actually exists, right? Let's say this is the wave function of a particle, and I know, and if you know that mod psi squared should be unity. Okay, mod's actually integration of this. Okay, mod psi square is the probability at any specific given x. So probability as a function of x is nothing but your mod psi x square, and we know total probability of finding a particle should be 1. Hence if you integrate this, or if you take the addition, right, so integration of px over x equal to minus infinity to infinity should be equal to 1. This particle must exist. That's the concept here, and that's what's the hidden being written here. Okay, so we just saw a finite infinite potential bulb, but it can have two flavors. So it's given by this expression, and you can see that there are two flavors. There's subtle difference between the two. Here the well, you can see it's infinite. This is rising to infinity, both of them. But here the well is between 0 and L. This is known as asymmetric well. Here the well is symmetric between around origin, right? This is known as symmetric well. How does it differ? It differs when you solve this expression. So if you see in the class, in the lectures, sir has solved this for this asymmetric well. There if you see, the answer comes out to be in terms of sin x. It's a function of sin x. Psi x is a function of sin x. Here it's not so. Here I'm not solving it, but it will be a function of sin x as well as cos x. You can refer to the book Streetman Banerjee, or any, you can just Google it. You will get symmetric potential well. Let's find this and see the difference between the wave functions. Okay, so this is a symmetric well. So how does this expression change? Again, psi x will again be 0 for x less than x minus L by 2 and x greater than equal to L by 2. This remains the same. So we need to solve only for, we don't know this, only for minus L by 2 to L by 2, and you know the potential is 0 there, right? Because this is 0. This is the well. So again the expression will become the same. I'm not going to solve it, but you can refer, equal to e times psi x. Solve this expression and you will see psi x will come as a function of something a sin kx plus b cos kx, something like that, and there will be other terms involved. This is what I'm talking about. This is not just odd function. This is sin is odd, cos is even. It's odd and even both. But in this problem we were given psi x equal to b cos kx for this, and I just told you that the particle must be found somewhere. So mod psi x squared dx from minus infinity to infinity should be 1. Why 1? Because particle must exist somewhere, hence it should be 1. For outside this box, the values of psi is anyway 0, so I can modify this integral to minus L by 2 to L by 2. This is the very important step. Please remember that. Because psi x is 0 outside, remember we had talked about it. This outside this box, because the potential is infinity, the particle cannot be found here. Hence this integral reduces to minus L by 2 to L by 2. Right? Now let me put the value of this minus L by 2 to L by 2. This will turn out to be b square cos square kx dx equal to 1. Right? And this is an even function, so I can just split it as 0 to L by 2. B square is a constant, will come out. Cos square kx dx equal to half. This is an even function, hence the positive side will give half, the negative side will also give half. So the integral will come out to be now 0 to L by 2 cos square kx dx equal to 1 over 2b square. Cos square so cos square kx. Now we need to just integrate this, so I'll write this as so cos square x can be written as, I think, so this is cos 2 theta is nothing but yeah, 2 cos square theta minus 1 divided by, yeah, that's it, because cos 2 theta is cos square theta minus sin square theta. So cos 2 theta, cos square theta minus sin square theta, and you can write sin square theta as 1 minus cos square theta, so it's going to be 2 cos square theta minus 1, and hence cos square theta can be written as, take the 1 to other side, 1 plus cos 2 theta by 2, hence I'll use the same thing here. So it will written as 1 plus cos 2kx by 2, 0 to L by 2, 1 over 2v square, and you can just try to evaluate the expression from here. I'm not solving this in the interest of time because I want to get to more important problems, but the concept here was very simple, and that was, there's a dx also here, okay, and the concept here was this, that the probability of finding a particle over all space must be 1, because particle must be either here or here or here, and we reduce it to minus L by 2 to L by 2 because particle cannot be found here, it can only be inside this box. All right, okay, so you solve this and you can get the answer. Okay, so now till this point of time we were talking about only the infinite potential wells. This was going up to infinity. This is different. Now this problem says, consider an electron with energy of 1 eV impinging at a potential barrier with V0 equal to 4 eV. This time it's not a well, it's a barrier, and width A, so this is given as 0.5 nanometers. Tunneling probability is given by, we'll see what tunneling probability is. Okay, so till now I have been talking about infinite well only, so you can see this is infinity, going to infinity, and this is the well. There is another flavor that can come. This means it is 0 everywhere and it only rises to a certain height V0 or certain time between 0 to A. This is a finite barrier. This is the question is talking about this problem. This is a particle in a box essentially. This is a finite barrier. This means there is no potential here, and due to there's some charge present or whatever, right? And you can see this potential barrier. This is some real life applications that we have here. Okay, and related to that is quantum tunneling. So this is very interesting now. So let's say there is an energy of this particle. Let's say this ball has some energy and you want to cross this. You cannot cross this classically because the energy is less than what's required. You can never cross it. So for instance, water, if the water has this much energy and this is the height of the dam, a water dam, water can never spill over. This is what classical, it says classically forbidden energy. Water will forever stay here if water is behaving like a particle, a water molecule, you can say. That's not true in quantum mechanics. Even so, you can say this is the wave that's coming, this is the incident wave, incoming particle wave function on your left, right? It can tunnel through. Tunnel means, although classically it was prohibited, it cannot cross this, but there is some probability. See, size there, size reduced, you can see psi has been reduced, but there is still some psi present here. This means there is still some, because note, probability is nothing but mod psi square. So if you integrate it in this region, you will get a non-zero probability. Here you integrate in classical, you will get probability equal to 0. This is 0 probability here in this region. Here it's not 0, there's some finite probability, reduced probability than this, yes, true, but not 0. That is called tunneling. This means rather than going from over the top like classical things do, you simply tunneled through this barrier. This is a barrier, right? So this is a barrier. Rather than going like this, red is classical, blue is quantum mechanical, you go through like this. This is tunneling. You're creating a tunnel. That's what this means. Okay, right. And mathematically it's been tunneling probability can be expressed as e to the power minus 2a, and I'm forgetting this term here. There's a there's some constant eta here. Okay, that eta is calculated as square root of 2 of, so this, the height of barrier minus the incident energy minus E incident over h cut. Eta is the, actually this whole term is the probability, and you can see that. You can calculate this, that's not a problem. Mathematics is fine. You can put the formula, you can calculate the answer. What's interesting is this. So you can clearly see the probability falls as you increase the width. So it's obvious. So here, if the width is small, and here if the width is big, probability is higher to tunnel through this, and it's very low because you have to dig for longer. Just understand in that manner. So if you increase the potential well width, the tunneling probability decreases. Secondly, you can clearly see that if I increase this barrier, right, if I increase this barrier to higher, probability should reduce, which it says so. If you increase V naught, right, there's a negative sign here. If you increase V naught, the probability also falls. On the other hand, this is the incident energy here. Particle is coming. If you increase the incident energy, the tunneling probability increases. So if you increase the E incident, eta decreases. If eta decreases, T increases, right? So you can just put the formula, you can just put the numbers in this expression, and if you find, I'll again in the next class I'll revisit this, right? That's not a problem, but my main interest here is to tell you what do each of these terms mean. Just use this formula, get the answer, that's fine. I think the answer for this is this. So you can just put the values here. H cut, you know, is I have told you h cut is nothing but h over 2 pi. 6.626 minus 34 pi, you know. V naught is 4 ev, E incident is 1 ev. Just remember to convert everything to SI units. It's very important. And A, you know, 0.5 nanometers, again convert into SI units. You can see it's 0.5 nanometers, right? And if you remember De-Broglie wavelength that we have seen in this class, it's 725 nanometers. I told you even if you increase the electron velocity, it will come out to be 7 to 8 nanometers, right? What's this A? A is not even 1 nanometers, it's 5 angstrom. So it's definitely lower than this, right? So De-Broglie, so all the quantum mechanical effects like tunneling will come into the picture. If this A was, let's say, 5 microns, you can clearly see this term will be huge as compared to 0.5 nanometers, 5 microns, 10 to the power 4 orders higher. The tunneling probability will be very close to 0, and that's what we see in classical mechanics. We don't see this because this A is so high in centimeters or meters, right? That T is so low, you never see a tunneling. Never see, you see 0 probability here. That's the idea. Any doubts for tunneling or the concepts that we had talked about till now? It can be a bit overwhelming, I understand that, because quantum mechanics, I did not understand it for the first 3 times. I have done at least 4 courses on quantum mechanics. For the first 2 courses, I did not understand. And I just could not understand the concept that why would a thing tunnel when you can stop it with a wall. The part I was not understanding, then I understood in this manner, that since this is a wave, a very not good understanding, I'll say, since this is a wave, it can simply go over this. That's how I understood it. Particle will always travel in the straight line, so it will hit the wall, it will come back, it cannot go here. But since it's a wave, I understood it, I rationalized it in the sense that in my mind, that since it's a wave, it will maybe go over like this, something like this. It's wrong, but at least I was able to convince myself that yes, some part of it will go to the other side and it can tunnel. Alright, any doubts, any comments? Alright, now let's move to some lighter stuff now. Okay. So in this problem we are required, I promised you in the start that we'll again get back to the bandgap thing. So we are back to bandgap. We will end this class where we started. The question are the bandgap of materials arranged in ascending order is. Just a second. Alright. So we'll arrange them, but first we need to understand what the bandgap is, right? What does the word band mean, and why is there a gap in that? Okay. So for that, I'll quickly take you a tour on the evolution of the bandgap, so to speak. Right. So we have seen this in the start. The semiconductors. Here again, you talk about metal semiconductor insulator. Hence, this is the conductivity that we see here, right? And one of the answer that was suggested that how do we identify semiconductor is we identify through this bandgap. Someone said that it's in the middle, right? We do not know what the word middle means. Here at least I can understand. It's, let's say, something between 10 to the power minus, conductivity is 10 to the power minus 10 to 10 to the power 5. Understand? But what does the middle band gap mean? You'll see in this problem. So what is a band gap in a semiconductor? Just you can simply understand that this is a simple drawing which is taken from Sheetman and Banerjee. So this is, you can simply understand, a 2D picture of the silicon atom. So each of this is silicon. Each of this is a silicon atom. Okay, and if you recall, silicon is atomic number is 14. That will be 1s2, 2s2, 2p6. That's 10. 3s2 and 3p2. So these will be your inner electrons or core electrons. These will be your outer electrons or shell electrons. That's what's called. Okay, so here, so it's you can see that it can donate, it can sp3 hybridization and all that. You can see it has four electrons in its outermost shell. In order to satisfy its valency, as someone pointed out in the very first slide, it will like to form covalent bonds. In this case, 4 covalent bonds. So each silicon is surrounded by 4 of its fellows. You can see this silicon 1, 2, 3, and 4. So its valency is satisfied and it will live happily ever after. That's the picture. Now I want to just focus, rather than being this 2D picture, I want to simplify it even more. Just focus on this line of silicon atoms. Just focus on this line of silicon atoms. I can draw them like this. So this is first silicon atom, second, third, and fourth. And you know that this is the potential energy. We know that the potential in an atom, it's a nucleus, it's positively charged. It will form something like kq by r, proportional to kq by r, where r is the distance from the nucleus. So if you see only this atom, and so it's falling as 1 by r. This is the parabola that I will see. Right, and it will be why it's negative, because I'm drawing the energies here, right? So energy would it will be k q1 q2 by r, where this is electronic charge, this is the charge in the nucleus. Okay, I'll draw this again, what I mean, because this is important. Why this energies are negative? Many times is a source for confusion. The potential created by the nucleus is positive. That's clear, because this Q is due to nucleus. This is potential energy. Okay, please understand that. So that will be, you know, that is K Q1 Q2 over R. Very simple formula. I'm not considering that there are other atoms. Just we'll apply the superposition. Just consider only this one atom. So Q1 is nucleus, which is positively charged. Q2 is the electron, which is negatively charged. Hence this whole term will come out to be negative. Hence you see this is V equal to 0. This is the infinite distance. Here the electron will be free. Here it's not free. Right? So what will happen? You can see that the if they are close enough, the potential curves of these two atoms are overlapping. How will the overall picture look? Overall picture will look something like this. Someone was asking, is it always rectangular? No, it's not. Now you can see this is a well here. Right? This is clearly a well. This is one well, this is second well, third well, and fourth well. They are not rectangular, they are hyperbolic in this case. Correct? So this is how the eventual picture will look like. Again, this is a 1D picture. Actually it's a 3D in real life, but here we are simplifying it. This is a 1D picture, right? And I can now alternately denote it like this. This is very similar to this. Just please note that this picture and this picture is effectively the same. You can see the nature of the curves. I have just for the mathematical ease, I have just treated them these curves to be rectangles. That's it. There's a periodicity to them, which we can see here, that after every a plus b it's repeating, and you can see the same thing happening over here. This is the Kronig-Penney model. You do not need to go into that, but I want to emphasize that this is the complete path that we are taking. Now once we know this, we know how to solve potential in a well. This is very similar. This is potential in a finite well. This is not infinity, but this is a finite well, and we can solve the Schrodinger equation. This is the potential that we have, and if you solve this, and this is the expression, this is the psi that you will get. On the left, you have when they are very spaced apart. This is an individual atom. This is atom 1 on your left, and atom 2. They are not interacting. No interaction. This means when two atoms are very far from each other, This is not the case for silicon or semiconductors. They are very close to each other. And in this case, what happens is that their wave functions, rather than being completely independent, this is called a symmetric wave function. This will be, you can say, a psi 1 plus b psi 2. Where a and b is some constants. This is psi asymmetric. This will be a psi 1 minus b psi 2. You can see the sign is flipped here. This happens when you solve the Schrodinger equation. You have to trust me on this. We'll come through this. Now, what's the effect of this? The effect of it is that the energy, rather than being saying the same like E0 or E1 or E2, it will create more states. You can see that this will become E2 plus delta E2 and E2 minus delta E2. This will happen for everything. So rather than being a single state, what you will start to see is that they will start to form a band. So let me draw this again. So rather than, this is E0, E1, E2, E0, E1 and E2. What's going to happen is that like this. Because there are so many electrons, so many atoms that are interacting with each other. This is just two. This is just, since there's only two atoms interaction, it can form E1 plus minus E1 plus minus delta E1. Two states. E1 has split into two states. Here there are n huge 10 to the power 22 number of atoms in the lattice. Hence this E0 will get split into n states. That's very huge. So rather than, so these levels, if I zoom in, this will be something like this. If I zoom in only onto this, these are individual spaces like this, but they are so close that you will see them as a band. Hence this term band comes in a band gap. And this gap, why this gap? This gap is already there. Remember, the energy is quantized because we are in a something close to a well, potential well. This quantization comes from this quantization, or the gap between the energies comes due to the fact that we are something of this sort of a potential. This gap comes from there, and this band comes when the two atoms come close together and their wave functions are split like this. And this is the complete picture how it looks. So you can see this is the band, first band, this is the second band, right, this is the third band, and so on, and there's a gap between them, right? Alternate way of looking that is that there are, when the R is far apart, right, these are your so this is your 3p electrons, this is your 3s electrons. They will not interact, they will stay away from each other. When you bring them close, their wave functions will overlap, and it will so happen that this is the upper band will have 4n states. Why 4n states? Because remember that 3s2 and 3p6, 2 plus 6, there are 8 states in total. 8 states and 4 electrons, only 4 electrons. So earlier 3s has 2n states and 2n electrons, which was filled. 3p had 2n electrons and 6n states, but when you bring them close, what's going to happen is that they will mix with each other, as you can say, hybridize, if you understand. It's not hybridizing, but I'm very simplifying it. So there will be 8 states and 4 electrons. What will happen? Naturally, every system will try to go to lowest energy state. Hence, all the 4 electrons will come here. No electron will go there. These are the 4n states. 4n states here. And there will be only electrons will occupy here. So there will be electrons here. What is n? N is the number of atoms. Number of atoms, which is 10 to the power 22 per centimeter cube. Such huge number of atoms. There will be electrons here, and there will be nothing here. At 0 Kelvin, when you increase the temperature, some of the electrons will go here, which we will see sometime later. So as you can see, this is how the reason for this band gap, the origin of the band gap. So what happens is that in metals, as someone had already pointed out, they overlap. So this is the valence band, the bottom one. The top one is conduction band. They overlap. So there are empty states. Here their electrons are filled, and here they are empty states. So they can clearly jump from here to here, and the current will flow, right? In semiconductor, this is the case. In insulators, this Eg is huge, like 8 electron volts, 10 electron volts, 12 electron volts. Like for, I think, silicon dioxide, which is an insulator, it's around 9 electron volts. Hence, this is an insulator. So this insulator, it's like 9 electron volts. So semiconductors, you can say, is 0 to maybe 6 or 4. That depends on definition actually. Some people draw a line at 8, some people draw a line at 6. Metal, there is 0, right? So band gap of materials in ascending order. So metal has the lowest band gap, then semiconductor, then insulator. So option A will be your correct answer. So in this problem, what we had talked about is the increasing sequence, so to speak, of the origin of a band gap. So remember that we started from a 2D picture, of very simple 2D picture like this. Then we converted to 1D picture, and then we see this in Kronig-Penney model. We see this kind of a potential, periodic potential, right? And we see that we see these structures like antisymmetric and symmetric wave functions when we are close, right? And that gives rise to bands. That gives rise to bands for every energy level. And why is there a gap between energy levels? Because we are still operating in something called the potential well kind of a thing, which we saw in the earlier slides, particle in a box, E0, E1, E2. Those energies were present. This is similar to that. And ultimately, this is again a similar problem approaching from a different band gap origin, explained using the electron states in this case. But the however you come to it, the answer will remain the same, that metal have 0 band gap, semiconductor have up to 4 or 6 electron volts, insulators have large, like 9, 10, 11, 12 and even more. Not infinite, I mean, you can say infinity, but above that you encounter that. But this is the line, this is where we'll draw the line. Okay, so as now we have talked about this cutoff wavelength that can be used for intrinsic excitation of a semiconductor material of band gap. So here we are talking about some material. This is the valence band, this is the conduction band. They say the gap, this is called energy gap, is 1.42 eV. I've been telling you there are electrons here, right? But they are bound here, they cannot move. They can only move when they go here. So if someone can provide them an energy to go from here to here, you'll see an electron here in the conduction band, right? And remember, in conduction band it is free to move. So if you see here, if an electron reaches here, it's free to move here, it can go, right? But someone has to do that. So this is one is called as excitation. Means you excite from a lower state to a higher state. Okay, why intrinsic? Sometimes the excitation can have many sources. So how do we excite it? As someone suggested earlier, it can be a photon, it can be thermal, right? These are the two major things that we encounter. Or sometimes it can also act due to impact, due to the momentum transfer. There are many things, momentum, some energy is also transferred, not just momentum. So so in this case, so usually when nothing is applied, thermal is always there, because where will thermal not be there? Only at 0 Kelvin it will be absent. At room temperature, which is 27 degrees Celsius or 300 Kelvin, you always have some excitation. So that will excite some of these electrons from here to here, right? So now we need to find what is the wavelength that is required. So that's very simple. What is the energy that you require? 1.42. Eg is h nu. So you see 1.42 eV equal to h times nu. So what we require wavelength. Okay, so so there is actually a direct formula for this, but I'll calculate first. So nu we can write as c by lambda. We have seen this earlier, right? Nu we can write as c by lambda. So lambda will come out to be hc by 1.42 eV. You can put the value 6.626 10 to the power minus 34 3 into 10 to the power 8 all SI units over 1.42 into 1.6 into 10 to the power minus 19, because EV I have to convert it to joules, hence I am putting the electronic charge there. All right, so let's just quickly calculate this. 6.626 times 3 divided by 1.42 divided by 1.6, the answer comes out to be something like 8.87 into, so that's minus 34, come out to be minus 26 minus 7. Okay, that's coming out to minus 7, and we need in microns, so this is meters. So this will come out to be 8.87 into 10 to the power minus 7 meters. This means 8.87 divided by 10 into 10 to the power minus 6 meters. This is nothing but microns. 0.887. Is there an option? Yeah, 0.87. That's the correct answer. So the takeaway from this is that we saw the origin of band gap. If somehow we can excite an electron, as someone talked about free electrons in semiconductors, at 0 Kelvin there will never be free electrons, because all the electrons will be in valence band at 0 Kelvin. Someone has to excite them to conduction band. That can be done using thermal excitation. Means when the temperature is risen from 0 Kelvin to whatever temperature. The higher the temperature, the more number of electrons will go from here to here. Or you can shine light. When you shine light, so electron here will gain energy. So this is the minimum. So this is the, at least you have to provide a light which has energy of 1.42 eV. At least 1.42. You can provide higher also. Then electron will jump from here and it will have some kinetic energy, or it can have some higher band it can occupy. Okay, but this is the takeaway from this. And similarly, a similar problem for this. What is the wavelength will be emitted by electron when transiting from minus 15 eV to minus 5 eV. So again, delta E you can calculate is, so final energy is minus 5 eV, initial energy is minus 15 eV, so energy gained is 10 eV. So 10 eV you need to just calculate what is the wavelength. So again you can just calculate the lambda. It's coming out to be same thing which we saw earlier, hc by delta E. Put this formula over here and you can calculate the answer. I think it's coming out to be 124, because there's a formula here, I think 12.4 divided by E. So there's something formula, you can just check the units there, but the idea is similar, that there in the previous problem we need to shine light from here to go to here. Okay, and you can just put these numbers over there and you can get the answer. I can just tell the formula in fact and derive that. It's not difficult. 6.626 10 to the power minus 34 into 3 into 10 to the power 8 divided by 1.6 into 10 to the power minus 19. This is the delta E, the energy that we are applying. And now we just have to solve this problem. So the numerator will be 20 divided by 1.6. That comes out to be 12.4. And this comes out to be minus 26 into 10 to the power minus 7 over delta E. Now you can put this in EV because you have already taken electron out there. So you can say 1.24 1.24 divided by delta E. You can put the energy here, and this will be in micrometers. 10 to the power minus 6 will remain, and you can get your answer. Okay, so yeah, that's that. Okay, so that's, now we have some time. Okay, so I'll do this problem in the next class, Fermi level, because I don't think in the lectures also Fermi level has been covered. So we'll do this 9th problem. This was the last problem. Yeah, this is the last problem. We'll do this in the next class. So that is all from me today. If you have any doubts or comments, you can ask me. I'll again reiterate my just to be clear that I'll post this whatever we are talking about on my YouTube channel, which I'm sharing the link for it now. And you can always write to me. I've shared my email ID with you. I'll stay back for some time. If you have any doubts or comments, feel free to ask. I'll stop sharing the presentation, but I'll be staying back. If you have any comments or questions, please go ahead. And thank you for your time.
So what is the difference between H and H cross?
Okay, so it's only a difference of mathematics. So H cross is nothing but H over 2 pi. Sometimes because 2 pi is a number which keeps on coming due to the fact that actually the reason I cannot recall exactly, but 2 pi is a number which you keep on listening for. Circumference is 2 pi r, and 2 pi is the number which keeps on coming. So sometimes, just to simplify that, rather than writing it 2 pi over and over again in our mathematical formula, some person said that okay, I don't want to write it again. I define a new entity H cross as H over 2 pi. That's it. H is the physical Planck's constant, and H cross is nothing but called, yeah, go ahead.
Okay, sir, I got it.
Okay, yeah. In the next class, again, I will try to revise some of the problems which we have talked in this class. that I'll do for the next sessions also. So whatever we talk about in the previous session, I'll give you a 5 or 10 minutes refresher that we had talked about this, and then only I'll build up on the next session, because sometimes it happens that there's a disconnect between the two sessions, and that becomes a bit problematic, especially for the people who are not able to attend every session. So that continuity is important. And as always, if you have any doubts, you can write to me, write on the forum, and I'll try to answer. I'll upload the video on this channel after some editing, and if you have some doubts, you can just go through that.